This video is about function composition. That's a function inside of another function. This is AP Precalculus topic 2.7. If you appreciate this content, please give it a like. Consider the function f of x equals 2x minus 3. Evaluate the following. F at 5 means substitute 5 for x. So this would be 2 times 5 minus 3. This is going to give us 10 minus 3, which of course is 7. We can evaluate at an unknown constant like f at c, even though we can't get quite as far. We just plug in c for x and we get 2c minus 3, and that's just as far as we can go. Notice that we can plug in anything. We can plug in a number like 5. We can plug in an unknown constant like c. We can do f at smiley face. This would just be 2 times smiley face minus 3. Similarly, f at 4a would be 2 times 4a minus 3. This one can simplify a little bit. 2 times 4a will be 8a. So we could write 8a minus 3. Follow this pattern with me. Students struggle with this last one. If f at smiley face is 2 times smiley face minus 3, then f at 5x minus 1 will be 2 times 5x minus 1 minus 3. We can simplify this a little. You can do the distributive property and get 10x minus 2 minus 3. Combining like terms, we get 10x minus 5. When you plug the output value of a function back into a function, it's called composite functions or function composition. For example, let g of x equal 3x plus 1. Let g at 2 equal c. Find g at c. To find the value of g at c, I need to know what c is. To find c, I need g at 2. So let's find g at 2. So g at 2 means plug in 2 for x. So this will be 3 times 2 plus 1. So g at 2 is going to equal 6 plus 1, which is 7. Remember, c equals g at 2. So that means c is equal to 7. That means g at c, which is what we are trying to find, is going to equal g at 7. So in other words, g at c is going to equal what we get when we plug 7 back into the function. So 3 times 7 plus 1. Therefore, g at c will equal 21 plus 1, which is 22. There are two ways that we can write composite functions. We can write it this way, or we can write it this way. Both of these would be read f of g of x. When working with composite functions, always start on the inside, or on the right-hand side. For example, if you are given f of g of x, you want to evaluate g of x first. Then use the answer from g of x and plug it into f of x. Example 2. F of x equals 3x minus 5 and g of x equals 2x plus 1. Evaluate the following expressions. Part A, f of g at 3. We're going to work from the inside out, so let's first evaluate g at 3. Plugging 3 in for x, we get 2 times 3 plus 1. That's 6 plus 1, which is 7. Now f at g at 3 becomes f at 7. Plugging 7 into function f gives us 3 times 7 minus 5. That's 21 minus 5, which is 16. And that's the answer. Part B, again, let's begin with the inner part. So let's evaluate f at 3. Plugging 3 into function f gives us 3 times 3 minus 5. That's 9 minus 5, which is 4. That means g at f at 3 becomes g at 4. So plugging 4 into function g gives us 2 times 4 plus 1. That's 8 plus 1, which is 9. And that's the answer. Part C, let's start with f at 4. Plugging 4 into function f gives us 3 times 4 minus 5. That's 12 minus 5, which is 7. So f at 4 becomes f at 7. Plugging 7 into function f gives us 3 times 7 minus 5. That's 21 minus 5, which is 16. Example 3. When we do f at g of x, we will get an expression, not a numerical answer. But first, I find it helps to go back to the smiley face. If f at x is equal to 3x minus 5, then f at smiley face is going to be 3 times smiley face minus 5. This just reminds us that whatever expression we have here, we do 3 times that expression minus 5. In part A, the g of x is like the smiley face. So again, f at smiley face is 3 times smiley face minus 5. So f at g of x will be 3 times g of x minus 5. But we know the expression for g of x is 2x plus 1. So this will become 3 times 2x plus 1 minus 5. For part B, think about what g at smiley face will be. G at x is 2x plus 1. So g at smiley face will be 2 times smiley face plus 1. Therefore, g at f of x will be 2 times f of x plus 1. F of x is the smiley face. But we know that f of x is 3x minus 5. So this will be 3x minus 5. These are both valid expressions. Sometimes you will be asked to simplify, or you will be given a multiple choice question with simplified answers. So be prepared to simplify by doing the distributive property, which would give me 6x plus 3 minus 5, and then combining like terms gives us 6x minus 2. Similarly, on part B, if I do the distributive property, I get 6x minus 10 plus 1, and then combining like terms, that's 6x minus 9. Example 4. Given the functions above, find the following. Part A, k at h at 2. Let's work from the inside out. We need to find h at 2. So plugging 2 into function h gives us 2 times 2 minus 3. That's 4 minus 3, which is 1. So k at h at 2 is k at 1. Plugging 1 into function k gives us 1 squared plus 4 times 1 plus 5. That's 1 plus 4 plus 5, which is 10. For part B, we begin with m at negative 1. So plugging negative 1 into function m gives us 3 times negative 1 plus 2. That's negative 3 plus 2, which is negative 1. So h of m at negative 1 becomes h at negative 1. it's a coincidence that this happens to be negative 1. Plugging negative 1 into function h, which is off camera, gives us 2 times negative 1 minus 3. That's negative 2 minus 3, which is negative 5. For part C, because we have an x and not a number here, we're going to get an expression and not a numerical answer. So this means the same thing as k of p of x. So p of x is this expression. So we're doing k of the square root of 3x plus 1. But k is this mess right here. Let's do a quick smiley face analysis, shall we? Since k of x is equal to this expression, k at smiley face is going to equal smiley face squared plus 4 times smiley face plus 5. That's just to remind you that whatever you have on the inside is going to be squared and then multiplied by 4 and then you add 5. So this radical is the smiley face. So we are going to get smiley face squared. So this is going to be radical 3x plus 1 squared. That's my smiley face squared. Plus 4 times smiley face. So that's going to be 4 times radical 3x plus 1. And then plus 5. So this is a valid expression right here. This does simplify a tiny bit, but to be clear, this is a valid answer. When you square the radical does go away. So you could write this a little bit more simply if you write 3x plus 1 and then plus 4 times the square root of 3x plus 1 plus 5. And now that I look at it, we can simplify a little bit more because we do have these like terms right here. So that's going to give you 3x plus 4 times the square root of 3x plus 1 plus 6. So this is a more simplified answer. Example 5. The function f and g are given by f of x equals x squared plus 1 and g of x equals 4x minus 1. Which of the following is an expression for f of g of x? I think I will color coordinate this one. So we're going to set up the outer function first, which is f of x. Because I know I'm going to plug something inside, I'm going to take that x squared and I'm going to write parentheses squared. I'm leaving space to substitute something in for x. But hopefully you can see that x squared plus 1 becomes parentheses squared plus 1. We're doing f at g. So we need to plug function g in right here. So that's why I'm going to have 4x minus 1 on the inside. So it's just a matter of simplifying this. Please do not think you're going to just square these two terms individually and maybe get 16x squared plus 1 or something like that. That would be wrong. That's a common mistake. Instead, please understand that you have to FOIL this. 4x minus 1 times 4x minus 1. So when you distribute 4x times 4x is 16x squared. And then 4x times negative 1 is negative 4x. And then when you multiply by negative 1, you get another negative 4x followed by a positive 1. And then I'm bringing down this plus 1. So this is going to be 16x squared minus 8x. I'm combining these like terms. And then plus 2. And then we suddenly realize that the answer is C. For example 6, we are given 4 different functions in a variety of formats, and we must use them to evaluate the following expressions if possible. For part A, we would normally start with the innermost function g at 3. However, here's function g, this table, and g at 3, meaning at an x value of 3, is not defined. There is no input value of 3. We'll say part A is not possible because g at 3 is undefined. Part B, please understand that this notation with the open circle is the same as h at f at 8. These two mean exactly the same thing. Either way, we need to start with f at 8. F is this graph up here. Here is an input value of 8, and this y value is the value of f at 8, which is -1. So we just found that f at 8 is -1. That means h at f at 8 is h at -1. H of x is this piecewise function. To evaluate a piecewise function, you have to decide which piece applies at the given input value. So which piece applies at -1? Well, the first piece of the piecewise function applies when x is less than 1. -1 is definitely less than 1, so the first piece applies. So we will evaluate h at -1 by plugging in -1 for x right here. So this will be absolute value of -7 plus 3 times -1. So that's going to be, I'll just show it, -7 minus 3. This is the absolute value of -10, which is +10. Part C, this notation g of k of 0 is the same thing as g of k of 0 like this. I feel like this notation makes it a little bit more clear that first we need to find k at 0. K is given to us as this description. K of x is a quadratic function with a horizontal translation of 2 followed by a vertical translation of -3. Because k of x is a quadratic function, it will be based on the parent function x squared. A horizontal translation of 2 will happen if we have x minus 2 inside the parentheses. Then a vertical translation of -3 will happen if we have a -3 on the end. So this is k of x. K at 0 means let's plug in 0 right here. That will leave -2 squared minus 3. -2 squared is +4, and 4 minus 3 is 1. So that is k at 0. Then g at k at 0 is actually g at 1, because k at 0 is 1. Oh no! It looks like this one's going to be undefined as well. We have to do g at 1, but we don't have an input value of 1 that goes with function g. Part D, f at 2. We work from the inside out. So first we need to evaluate f at 2 if we can. This graph is function f. Here is an input value of 2. Is it going to be 1 or 4? Well, the open circle means that it's not really defined there, so it will not be 4. The closed circle means that this is the value of f at 2. So f at 2 is 1. That means f at 2 is f at 1. Back to the graph. Here's the input value of 1, and here is f at 1. F at 1 is 4. That's the final answer. Part E. First, we need to do this part and find h at 1. h is the piecewise function. Which piece applies at an x value of 1? Well, the domains over here tell us that when x equals 1, this middle piece applies. In other words, h at 1 is simply -4. For the next step, I'm just going to convert this to the equivalent notation. Remember, with the open circle, this means the same thing as g at h at 1. And we just found that h at 1 is -4. So this is the same thing as g at -4. G is the table up here, and g at -4 is pi. Kabam! Part F. I mean, what the heck is this? Seriously. Alright, well let's break it down piece by piece. We're going to work from right to left. So first we need to find k at 3. I'm going to put it way over here so we have lots of space. K is this quadratic function that we invented. So k at 3 means plugging in 3 right here. 3 minus 2 is 1. How much of this do I feel like showing? So I guess I'll just go ahead and show 3 minus 2 squared minus 3. And then this is 1 squared minus 3. But this is really just 1 minus 3, which is -2. To continue on, we basically replace the k at 3 part with -2, and we bring down the g at f at h. So, in fact, long strings like this are the benefit of this open circle notation, because you can simply work from right to left and evaluate one at a time, bringing down the rest. So, it's time to do h at -2 now. Let's see, h is the piecewise function. -2, we're looking for h at -2. -2 is less than -1. That means the top piece applies. So we're going to plug in -2 right here. So we have the absolute value of -7 plus 3 times -2. So we have the absolute value of -7 plus 3 times -2. That's the absolute value of -7 minus 6. That's the absolute value of -13, which is positive 13. We just found h at -2, which is this part right here. So we can replace h at -2 with 13 and bring down the rest. So this is going to become g at f at 13. We replace h at -2 with 13 and bring down the g of f part. But now it's time to do f at 13. We continue from right to left. So now it's time for f at 13. F is the graph, and f at 13 is off the chart. So in other words, f at 13 is undefined. We made all of that progress only to find out that the composite is undefined. Example 7, two functions f and g are composed such that f of g of x equals 4 times the square root of x minus 3 plus 2. Which of the following could be expressions for f and g? Let's try them out one by one and see which one gives us the right answer. So for option A, f is the square root of x. So that would be the outer function in this case. So we start by putting a big old square root of x. And then the inner function is g of x. So that's going to be 4x minus 3 on the inside. That is not a match. Let's try option B. F, the outer function, is 4x minus 3. So we would write 4 parentheses minus 3 for function f. And then function g, the inner function, is the square root of x. So that would go inside the parentheses like this. Not a match. For option C, the outer function is the square root of x minus 3. So that would be the square root of parentheses minus 3. That's function f, ready to plug something into it. And then function g is the inner function, which goes inside the parentheses. So the 4x plus 2 would go like this. We could simplify this a little bit, but there's definitely no 4 outside the radical. There's nothing being added on the end of the radical. It's not a match. By a process of elimination, the answer is D, but of course we will follow through and show why. The outer function is f, 4x plus 2. Let's write this as 4 parentheses plus 2, so we have something to plug into. And then the inner function is the square root of x minus 3. That's what goes inside the parentheses. Square root of x minus 3. This is equivalent to this. We don't really need the parentheses at this point, so this would be the same as 4 times x minus 3 plus 2, and we do have a match. Example 8. The functions f and g are given by f of x equals 1 over x, and g of x equals the square root of x. What is the domain of the function h given by h of x equals f at g of x? Start with the inner function, which in this case is g of x. Any restrictions on the inner function will automatically be restrictions on the overall composite function. So g of x is the square root. You cannot take the square root of a negative number. In other words, for g of x, we have the restriction that x must be greater than or equal to 0. It can't be negative. The limitations of the inner function automatically become limitations of the composite function. So h of x must be greater than or equal to 0 so far. There may be more limitations, but this definitely applies. So we can eliminate all real numbers because we have this limitation. Let's see, all real numbers not equal to 0. Nope, that's too broad. That would include negative numbers, and we already know that can't be. So we've narrowed it down to either C or D. Let's see if the outer function f will introduce some new limitations. If I was only talking about the restrictions on f of x, and I didn't care about g or h, I would say, x cannot be 0. You can't divide by 0. That would make it undefined. So I would say I have this restriction, x cannot equal to 0. But I need to be careful here because we have already used x when we were talking about the inner function g. So this is different. For the outer function, let's talk in terms of f at smiley face instead of x. I don't want to get this x and this x confused because they're not the same thing. F at smiley face will be 1 over smiley face. So the restriction is smiley face cannot equal 0. That's not a smiley face. Smiley face cannot equal 0. Now I said temporarily smiley face. What do we really have in here? Instead of smiley face, it's really g of x. We can say f at g of x is 1 over g of x. The denominator cannot equal 0. That means g of x cannot equal 0. But wait a minute, g of x is the square root of x. So that means the square root of x cannot equal 0. We need to solve this for x. If we square both sides, we get x cannot equal 0. Let's combine these two restrictions. X has to be greater than or equal to 0, but wait, x cannot equal 0. That means x has to just be greater than 0. So the answer is C. Soak that in. Example 9. The piecewise linear function f, defined on the closed interval from -4 to 4, is shown in the graph. The function g is given by g of x equals x plus 3. Which of the following is the graph of y equals f at g of x? Since g of x is x plus 3, then f at g of x is really f at x plus 3. Think of this in terms of transformations. This is a horizontal translation of f of x by -3. So the question is, which one of these options is the same as f of x, only shifted 3 units to the left? If we shift f 3 units to the left, instead of going from -4 to 4, it will go from -7 to 1. And that is what we see in option A. Example 10. The function p, not shown, is a polynomial function of degree 3. The graphs of 4 functions f, g, h, and k are given. The output values of p are the same as the output values of the composite function when p is composed with one of these functions as the input function. For which of the functions is this statement true? So they are telling us that p of x is some cubic function. We don't actually know what it is, but I'm going to use x to the third power as an example. And they are asking us, is p of x the same as p at f, or p at g, or p at h, or p at k, these composite functions? Are any of these the same as the original function? I think the answer is going to be A, but let me show you why all of the other answers are wrong, and then I'll circle back. We should be able to easily write a linear equation for the graph of g of x. Let's see, I'm thinking y equals mx plus b, so y equals, the slope is -1, so that's negative x. The y-intercept is 0, so that's it. Y equals -x. Now, let's write this in function notation. So, what we have g of x is equal to -x. I'm writing it this way so we can analyze the composite function p at g of x. P at g of x will become p at -x. Is this the same as p of x? Question mark. Think of your transformations. We have learned that a negative sign in this position is a reflection of p of x over the y-axis. So this will not be the same. This is the horizontal line y equals 1. In function notation, we have h of x is equal to 1. Now let's think about the composite function p at h of x. This is p at 1 because h of x is equal to 1. Will p at 1 equal the original function p of x? No, p of x is some type of a cubic function, but p at 1 is just a constant. Right? We're just plugging in a single number. So that's just going to be a constant like skirt. So that's not going to be the same. It'll be the exact same thing for k of x. This is y equals 0. In function notation, k of x will equal 0. So the composite p of k of x would just be p at 0. That's just a constant. There's no way that's going to equal the original cubic function p of x. This has variables, this doesn't. Let's go back to the graph of f. This is the line y equals x. Y-intercept of 0, slope of positive 1. This is the line y equals x. In function notation, we have f of x is equal to x. Consider the composite p of f of x. Well, f of x is x. So if I plug that in, I get p of x. So, of course, p of f of x is equal to p of x. The composite is equal to the original function. The function f of x equals x is called the identity function because if you take the composite of any function with the function f of x equals x, you just get the original function back again. Number 11. The table gives values of the function f for selected values of x. The function g is given by g of x equals x squared. Which of the following gives values of g of f of x for x equals -1, x equals 0, and x equals 1? The table gives us the values of f of x at -1, 0, and 1. I'm just going to copy it sort of vertically. So at -1, f of x is 0, at 0, f of x is 1, and at +1, f of x is -1. Our goal is to find the value of the composite function g at f of x. So I need to do g at 0, g at 1, and g at -1. But don't forget that g is just x squared. So I'm just going to square all of these. So 0 squared is still 0, 1 squared is still 1, and -1 squared is also 1. So the answer is C, 0, 1, 1, 0, 1, 1. Hey guys, don't forget to like and subscribe, but also if you found this video helpful, there's a lot more where that came from. You can click the upper link, which will take you to the whole unit playlist, or you can click the lower link, which will take you to the next video in the playlist. See you there.